Welcome back, friends, to another session of finite element methods for fluid dynamics. In the last session we started talking about vector spaces and how we are going to use them in this course. We would like to continue on that, but before that I want to give you some ideas about Ax equal to b, the linear equation system. So let us consider a linear equation system which we are all very familiar with, Ax equal to b. A is a matrix which is given to us, b is the force vector, it is also given to us, and x is the unknown. So the challenge is to find x, and as we all know, x is simply given as A inverse b. So for simplicity, we are going to consider a square system. So this is a system where we have n equations and n unknowns. So n equations and n unknowns, which means the size of A is of the order n by n. If I look at the size of B, that is actually a vector. So let me call this as Bi, and this is of the order of n rows and 1 column. And likewise I can talk about x, which is also xi, in fact this would be xj, n cross 1. Now if I want to solve this equation system, there are many methods that you are already aware with, okay? And in fact we are going to look at some of them as your home assignment problems. But I want to talk about a very interesting concept which is related to the conditioning of the system. So I want to discuss a little bit about ill conditioning. And this is very important when we talk about numerical solution to this problem Ax equal to b. So let us define a residual. So R is the residual vector, and that is given as b minus Ax. Okay. As you will see, if x is exact, in the sense that x is actually the exact solution of Ax equal to b, then it implies that my residual vector is identically 0. So I can talk about the size of the vector r. In fact, if you remember, we can talk about the norm of r, and norm of r would be 0. So the length of this vector would be 0. That is for an exact solution. But suppose my x vector is not the exact solution, there is a little bit of deviation from the exact solution, then r is not exactly 0, it is non-zero. And it would be interesting to see what does r being close to 0 imply. So our common sense tells us that whenever r tends to 0, that means we have close to an exact solution, and I just want to caution you about that. So let us look at some examples. So first I want to talk about what is meant by a well conditioned system. So Ax equal to b is a well conditioned system of equations if small errors in A or B or in the solution process have only a small effect on the solution x. This is really the ideal situation, that if I have a small error either in B or in A, as some kind of an approximation, or when I try to solve the solution approximately, then the change in the answer with respect to the exact answer should be also small, of that order. Okay, so that's well conditioned. If that doesn't happen, then we have an ill conditioned system. So the system is ill conditioned if the effect is large. Let me give you two geometric examples, and I will consider a 2 by 2 system. So consider n equal to 2, and this is simply because I want to use geometry to push this idea. So let us say I have an equation system which I can represent in the xy plane, since n is equal to 2. So we are talking about two lines. So this is equation 1, this is equation 2, and their intersection would give me the answer. Okay, so this is situation 1. Let me consider another situation, again on the xy plane, and this time the two equations that I represent, they also form two lines, but consider that the slope of those two lines are close to each other. So let me draw those lines. So this is equation 1 and this is equation 2. So let me mark this. This is equation 1, this is equation 2, this is equation 1, this is equation 2. The slope of the two lines are different. The slope of the two lines are very close to each other, they are almost parallel. Notice, if the equations are such that the two lines are parallel, then of course they will not intersect unless they are coincident, and in that case you do not have any solution, right. So this we are talking about really a very strange case. Now the problem is, as soon as I shift line 1 or 2 by a very small amount, a very tiny amount, you will see that there is a huge change in this solution. So this point represents the exact solution x0, y0, but if I shift the line 2, let us say a little bit to the right, okay, just a little bit, then you will see that the intersection point moves substantially and I would get a large change in the solution. Let me give you an example, a numerical example. So let us consider this system 0.9999x minus 1.0001 y, this is 1, and I take another equation which is x minus y, this is also 1. So for this the exact solution is x equal to plus 0.5 and y equal to minus 0.5. Okay. In fact, notice that these two lines have a slope which is very close to x equal to 1. In fact, the slope of this line, the second one, is exactly 1. So it is at an angle 45 degrees to the x axis, and the other one is also a very similar slope, just a little bit different than that. So it is really an example of this situation. Let me now give you another system and compute the solution to that. So let me perturb this quantity, the right hand side, by epsilon. Okay. So consider 0.9999x minus 1.0001 y equal to 1. So first equation remains the same. The second one remains the same, but I perturb the right hand side by epsilon. So here RHS of equation 2 is perturbed by epsilon, a small number. So this has a solution which you can calculate. X is 0.5 plus 5000.5 times epsilon, and y has a solution minus 0.5 plus 4999.5 times epsilon. And what is intriguing is, of course, if my epsilon is 0, I get back my original solution, okay, as expected. But consider any other value of epsilon. This solution is amplified by, or the change in the solution is amplified by almost 5000 times. So let me write that down. That solution is amplified nearly 5000 times epsilon. So any error that I incur in my variables here, because of the nature of the system, I get a very large amplification in the error. Okay, that's no good. That's something to be wary of. So this is an example of ill-conditioned system. We can actually generalize this to higher dimensions. I have shown you this only for 2 dimensions because the geometry is easy to handle, but the same ideas would also hold for higher dimensions, in 3 or n could be anything. So the question is, how do you ensure that you have a well conditioned system? I am not going to go into the details. Of course, there is something called the condition number, which depends on the eigenvalues of the matrix A, and one can easily show that, but I will give you a thumb rule that usually if diagonals of A are large, compared to off diagonal terms, then A is well conditioned. Okay, and you can look at this system. Okay, these are the diagonal terms, and they are really not much larger. In fact, they are comparable to the off diagonal terms, and that is one reason why this system did not turn out to be a well conditioned system. So we have to be very careful. Remember what I said in the beginning, all numerical methods which are trying to solve partial differential equations would ultimately have to solve Ax equal to b, and we are dealing with an approximate solution. So we want to ensure that the system is well conditioned. So the Ax equal to b that we generate out of our numerical method should be a well conditioned system. If it is not, then it is prone to these very strange situations where a small perturbation in the data would lead to very large changes in the solution. What are the symptoms of ill conditioning? So, typically what happens if you have determinant of A, this is small compared to the max absolute values of A ij or the matrix A. And then what happens if I look at A inverse is going to have large absolute values compared to the absolute values of the component of or components of the solution. Okay? And therefore, what will happen is the residual may still be small even if the solution is inaccurate. I think it is best illustrated through an example. So, I will show you this and then elaborate on what we are looking at. So, let me look at this system which is 1.0001 times x plus y, this is 2.0001, and the next equation is x plus 1.0001 y, this is 2.001, and I am trying to find out the exact solution to this problem. So, the exact solution is given as 1 1. In fact, you can see it from inspection. If I put x and y both equal to 1, this equation is satisfied. Great. Now, let me try putting into this equation a very approximate solution. So, try a very approximate solution which is 2 and 0.0001, and I want to show you what this leads to. So, remember we talked about the residual. The residual is essentially b minus ax. If x is the exact solution, as we talked about earlier, the residual should be 0, and of course, if x is not exact, then this right hand side will not be 0 and the residual is finite. So, intuitively one hopes that as you depart from the exact solution, you would get a large residual. Okay? So, suppose I restrict myself to 4 decimal places. Because I am dealing with an approximate method. Okay. Let us calculate the residual. So, R is going to be given as B, and in this case B is this quantity 2.001, 2.0001 minus A. So, let me form this A for you. This A is 1.0001, this is y, coefficient of y is 1, this is 1, again 1.0001, and times the x. So, I am going to take the approximate x, which is 2 and 0.0001. Okay. Now, one can estimate what is this quantity over here. A times the approximate x. So, let me just write this down for you. You can calculate it very easily. So, this multiplies this multiplies this. So, on the upper row I would get 2.0003, okay, and in the lower row I am going to get 2.0001. So, I am approximating this is 2 and this is 1.0001 times 10 to the minus 4th. So, I have just approximated it to 4 decimal places, I get this, and therefore, my residual is the difference of these two quantities, and that turns out to be minus 0.002, and the lower one is actually 0.000, because I am calculating only 4 decimal places. And you see, you are fooled into believing that your residual is close to 0. Okay. Note, even though the approximation is bad, okay, it is too far away, a naive person may think that this is okay. Right? So, if you just looked at the residual and you kind of see, all right, up to 4 decimal places the residual is very small, and therefore, this is an acceptable solution, you are doomed. This is not the exact solution. I mean, the exact solution was 1 1. Okay. So, why did this happen? It is actually a fallout of ill conditioning, and that is what I tried to explain you, that when you have in A inverse you have large absolute values compared to the values of the solution, then the system will fool you to kind of show you that the residual is small even when it is not. So, the bottom line is, I just wanted to convey to you that we should be very careful in terms of finding solutions of Ax equal to b, and the condition number of A, which actually depends on the ratio of the largest to the smallest eigenvalue of A, is manageable. It should be as close to 1 as possible. If you have an ill conditioned system, then things like this can happen. So, one thing we want to strive for in this course is that the formulations that we come up with to solve the partial differential equations, they should have Ax equal to b with good condition numbers. Okay.